Okay, this is this space problem that we're talking about here, when we have the poles that are slightly in the right half plane and a nominal value of 100 for the pitching. We want to pitch this it's a spacecraft, this GPS satellite, to keep it pointed towards the Earth. So, as with the aircraft case, I have these two unstable poles shown here in MATLAB. And if I put an actuator with a programmable 0 at 2, so I have s plus 2 over s plus 20, I'll have an open loop system as shown here. And if I size-o-tool this, the size-o-tool shown on the left looks pretty decent. If I raise the gain, it looks like I can get my bandwidth and frequencies that I want with pretty decent phase margins. However, in fact, you may want to push this so you get the maximum damping right there, and it's going to give you a crossover frequency of almost 10. But again, you are feeding back theta. So as long as you recognize that and dealt with that, that's fine. But this is what you would get if you fed back theta. We, however, want to feed back pitch rate, which means our gyro. We have to use our gyro. So if I were to feed back my gyro into my size-o-tool, then I'll get something that looks like this, because there's going to be a 0 put at the origin, which is right here, and the double pole will then go around. If I raise the gain, I'll go up and then back down, come to the real axis, and go into those respective zeros. And of course here on the other side I can vary my... And so if you fed back theta, the angle, and received the size-o-tool on the left, then you would have had to explain why you did that. And some groups did that, and they were maybe just lost a few points. However, otherwise you would have had a 0 at the origin, and if you try to sneak that by me, you lost almost 10 points on that. The other thing that's interesting to notice is that you notice that even though I have stable system here after with root closure, because of the unstable poles, the MATLAB gives me a negative phase margin here, where I can see that obviously if for example, this is my crossover frequency, I have a pretty decent, I have a 90-degree phase margin here at that crossover frequency. And of course I can lower that down to here or so, but even here, if my crossover frequency is say 6 or 7, I still have a phase margin of over 90 degrees. And notice I'm getting -3 and minus gain margins. So you have to watch MATLAB. I don't know why it makes these errors, but you have to check it constantly. At least that's been my experience. Okay. Another problem is that the spacecraft was supposed to follow a ramp command. And you know, in order for a ramp command, the output to follow a ramp input, you have to have a type 2 system. Now some groups recognize this. Other groups said this, but then they kept a type 1 in the forward loop. So you need 2 integrators, 2 S's, in order for this to follow a ramp input. No matter how the graph looks, you need that to have that. Now I realize that this test was time sensitive, but let's just look and see that what these block diagrams mean. In the first case, for this particular one, we have a step input with the ramp somehow occurring over here. Now I hope that you see that the way to implement a ramp input is either to put a 1 over s right after the step. So you have a step going to 1 over s, a ramp input, or to select a ramp input from the options that are available to you in Simulink. So, the problem with all this stuff on the output side is, I hope that now you realize, at least look at this diagram here and realize with the corrections, that you can't do any of this without theta. Where is theta coming from? The whole Lab 2 exercise was to show you that you don't really have anything to control your system with except that gyro. You have theta z dot. So where am I going to get theta? Now you might say, well, I have a theta sensor. Okay, then you have a theta sensor. Well, then you'll have theta over here. But how is this going to operate? This is nature on the output side. This is all abstract mathematics. This is if we want something physical to hold in our hand, it all occurs over here in the input side. Here's where the gyro output comes in. Here's where our input comes in from the stick or from an electrical command. We generate an error signal. The error signal goes through some compensation that we've built into an actuator and supposedly time delay to operate the plant. But all the plant outputs, and I want to emphasize this at this point of your, at least for the space people who are watching this, you don't have any of these outputs. These outputs are all abstract quantities. You could call them mathematical outputs. So if we had a computer, we could compute what we think they are. But the only way to get a handle on these outputs is to measure them. So we have measured them with an actuator, or a gyro. So we have a gyro that will give us theta z dot if we mount it on the correct axis. If, however, you feedback theta, then you would have to have a theta sensor. And they do have theta sensors. Or, as we mentioned in the aircraft case, you could actually feedback the integral of theta z dot. So if you call that signal q, then the integral of q dt, that integral would be available to you as the output of the gyro to feedback as an additional input. And if we look at time delay one more time, here we have a system where the group is saying that the lead lag has a larger time delay than the PID, when what they mean is that it has a larger delay margin. You really must understand the difference between time delay and delay margin. Delay margin is it is not time delay. It is the max allowed time delay, right? So a large delay margin, a high delay margin, big delay margin is a good thing. It's the max allowed time delay. Time delay itself is always adverse. It's always bad. So be careful when you say that the lead lag system has a larger time delay than the PID. If you mean has a larger delay margin, you're actually saying the opposite to the customer. Okay. And another thing is, I don't know, I didn't go into the MATLAB code for a lot of you, but for example, here's the original and the time delay signals. So you have the time delay signal with leading the time. So there has to be something wrong here. You need to explain this. I mean, the time lag, the phase angle must always decrease for a signal with time delay. It's e to the minus tau s. So this is how can we increase phase by adding time delay? So this always costs you, at least for not recognizing this and possibly not going back into your code and finding the error. Finally, here's another example of a improper use of a time delay. This is in Simulink, and of course it's outside the inner loop where the time delay belongs. But I don't know how you could show the phase lag and the frequency domain by putting this into a time response. So this, again, Simulink is used for simulation, usually for time simulation, very seldom used for analysis. And if you can show me how this variable time delay here helps with analysis, I'd be glad to know. But what you want to do is to put something, a mathematical function in here in the inner loop, so that you show with phase lag occurring as frequency increases. That's the way to do it. That makes sense, physical sense. So one final time to take a look at the space exam. You assume that you had an actuator, and of course you're going to feedback your pitch rate from your gyro. If you fed back theta and made the problem easier, that's okay, but it would have required some discussion and probably cost you some points if you didn't convince me. 40 points for the cast design. Almost everybody got the cast design fine. We had the replacement of the PID, and very few groups showed me how they replaced their PID compensator, so that might have cost you some points if you didn't show me how to do that. And the time delay, if you confuse time delay and delay margin, you lost some points over here. Or if you show the phase, if you showed the phase angle increasing with time delay and with frequency, that's impossible. Or if you blindly use the variable time delay in Simulink without understanding how that affected the analysis, that also affected you. And then there was extra points on equivalent time delay and sensitivity function. And almost everybody got at least 5 points on this part of the exam. Okay, that's it. Thanks very much.